how the hell do they know to be the same temperature as each other to 1,000th of a degree? In this room, the temperature fluctuates by degrees.
Exactly.
The whole universe is that. When the universe was small and all talking to itself in equilibrium, temperature equilibrium, then it quickly expanded.
Hence, the justification for inflation.
Yes.
Right. Because all of that expansion all at once it gives you the uniformity across the entire expansion.
Correct.
Wow. Okay, I'm done.
No, we need you, Chuck. Chuck, it's a cosmic queries.
This is crazy.
Come back. This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. We're doing cosmic queries today, and guess who brought them all? Chuck. Nice, Chuck, man.
Hey. That's right. I bought the goods.
You brought the goods.
Yes, I did. We got everything that you ever wanted to know, and I'm going to read 4 of them because that's how many we get.
But I think, but they're very fleshy replies when we do that.
The way I look at it is, we have a reservoir of inquiries, and that gives us fodder for discussion, and eventually all of these questions will be answered.
All right, and these questions all from our Patreon supporters.
Absolutely.
We love them.
But we love.
We're going to do cosmology today.
Oh, I did my hair very special today. So I'm very happy about that. I'm glad that we're doing cosmetology.
Cosmetology, yeah. That's what it is. So we've got with us today one of the most active scientists in that space, the space of cosmetology. Brian Keating. Brian, welcome to StarTalk.
It's nice to be with you in person finally.
Right, yes. You're active on social media, and I was honored to be a guest on your podcast.
Yeah, two-time guest, yeah.
Two-time guest. And what's the name of it?
It's called the Into the Impossible podcast, named after Arthur C. Clarke's famous dictum that the only way of discovering the limits of the possible is to go beyond them, into the impossible.
Ooh.
Oh, yeah. Did he realize that once you get into the impossible, it is the possible?
Well, I don't know if you realize that.
Don't be too rational about this, Chuck. You've been thinking about cosmology, especially signatures of the Big Bang.
Yeah.
Your whole career.
Yeah, this is what I've been doing. I dedicated my life to understanding, what happened on the Tuesday before the Big Bang. Can you answer that question? Not really sure.
Tuesday. Wait, let me get your pedigree out of the way here.
Yeah, of course.
So, you're Chancellor's Distinguished Professor of Physics in the Department of Physics, UC San Diego.
That's right.
But are you the student's Distinguished Professor of Physics?
Well...
I don't care what the Chancellor thinks of you.
Wow.
I just teach to him.
No,
he's
right. You go to his office, you get private lessons.
That's funny.
You're also principal investigator in the Simons Observatory.
That's right, yeah.
We've got a whole Simons thing down here in the city.
Yeah,
at the Flatiron Institute.
That's right, yeah. Jim is a titan of the city. Fortunately passed away last year, age 86.
Jim Simons.
Simons, he's a philanthropist, a mathematician. He had multiple careers. He worked for the government. He broke codes during Vietnam.
You said philanthropist and mathematician, but not in that order.
Not in that order. And also,
I left out one thing. Reverse order.
I left out one thing. A hedge fund manager, 26th richest person in the world. But one thing that's most important, I left out, is that his wife, Marilyn Simons, has the distinction and honor not only of having an asteroid. I mean, a lot of people have asteroids, but we got an asteroid named after Jim.
Anybody's got an asteroid.
Yeah, exactly.
Well, yeah.
Duh.
But Marilyn...
let's be honest. The solar system is littered with them. They're basically space garbage. Let's be honest.
Can't give them away.
Right. It's just the man who does not have an asteroid.
Join you and me both. I don't have one either. But Marilyn has the honor, the distinction of being one of my first babysitters. So she got early experience with dark matter.
Wait, she changed your diapers?
That's right. Dark matter is where she got her experience with
Wow.
Yeah.
age 2 or 3, yeah.
Wow. So you guys go way back.
Way back. Before the birth, before my own personal Big Bang, as Chuck said 9 months earlier.
So what's up with the Simon Observatory? What's your relationship to it again?
So I'm what's called the principal investigator.
Okay.
So I'm the co-founder of it, along with your friend David Spergel.
Yeah.
And Mark Devlin.
We came up together in graduate school. And yeah. David Spergel is on an earlier episode of StarTalk
exactly.
as the chair of the committee representing NASA investigating UAPs.
UAPs, yes.
Yeah.
And he's
Check that
also
out in our archives.
He's also he took over from Marilyn Simons as the president of the Simons Foundation.
Okay.
So he had to kind of withdraw from the Simons Observatory, otherwise he had conflict of interest.
Conflict of interest? Is
I
that
mean, what is that? Is that a thing?
Is
now?
that what?
Really? For people like David, yeah, very ethical people, yeah. So, so in 2014, in this very city, there was published in the front page of the New York Times on March 17th, St. Patrick's Day, was published an article that said, "Space ripples herald the origin of the universe." And it was an announcement that the BICEP 2 experiment had detected what are called gravitational waves, primordial waves of the ripples of space-time.
So BICEP, that's an acronym. What's that acronym for?
I created the acronym. It was a background imager of cosmic extragalactic
I'm
polarization.
just checking his BICEP.
Yeah, exactly.
You want something?
Exactly. Oh, look at those.
I don't discriminate.
The biceps. What's
right,
it looking at? Space guns.
Guns. Okay, so give me back the acronym.
The Space Gun Show. As seen by the bicep.
Background.
Imager of cosmic extragalactic polarization. Now, why is that so clever? Why is that not just a dad joke? Well, the signal that we're looking for is called polarization. And that polarization pattern, if you were to be able to see it with special polarized glasses, we'll get to in a few seconds, you would see a swirling, twisting, or curling pattern. So I wanted to make bicep the muscle that does curl. And I got away with the dad joke even before I had kids.
I see what you did there.
See that?
See what you did there.
That's not bad.
The curl
I gotta tell you.
is only exercises one muscle.
Yeah,
that's right.
No
That's
other
it.
muscle.
Nothing else.
Curl is the
That's
bicep.
That's right.
All right, very good.
So yeah.
So what were you on that project?
I founded the previous predecessor experiment called creatively Bicep 1, the first incarnation of it. And just like with your iPhone, every couple of years you upgrade it, you get more pixels, you get more data. But the cool thing about it, literally, it's at the...
So it's in orbiting.
No, it's in the South Pole, Antarctica.
Oh.
So it's at the very bottom of the
I knew
world.
that.
Yeah.
Oh my gosh.
Yeah, that's right. And so
Penguins would call it the top of the world, but
that's right. I don't want to be too, polar bear specific, centric. So I created that experiment along with my late great colleague and mentor Andrew Lang. Tragically took his own life soon after we got our first data from the second version of the experiment, but that's another podcast. But that experiment was built intently to do nothing else but measure these waves of gravity if they existed. And we thought, we'll never detect it. It's minuscule. We're looking for signals that are 1 billionth of a Kelvin above the CMB's average temperature, which is 2.7 Kelvin.
Right.
So it's a minuscule. We didn't think we'd do it. We had to try it, though.
So the challenge there scientifically is to see a signal that low, given the fluctuations that are already there.
And the Earth. And the atmosphere. Yep, exactly.
All radiating into the experiment.
That's right. Exactly. Yep.
It's literally like a string with a bell on it.
But the crazy thing is, in 2014, we announced we did it. We saw this kind of needle, it's actually like a piece of hay in a haystack. It's so.
Can you find the hay in the haystack?
That's funny. Piece of hay. That's
what you do with the needle? Actually, Iron Man said this in one of the movies, but we all knew this.
Right.
Okay, if you want to find a needle in a haystack, just burn down the haystack.
Right.
And the needle's left.
And then that's all right, because needles don't burn.
Or take an electromagnet, and you'll find the needle like that.
Yeah.
So this experiment was designed to do one thing only, and we never thought we'd do it. If we detected it, we'd be, kind of, the onus is on the experimentalist. You want to know enough that you can detect it, but you have to, not fall victim to the most pernicious of all scientific fallacies, which is confirmation bias.
Right.
You're looking for something. Oh, you found it. Eureka.
Right, that's what
that never happens, right? But we did. We found it. And I remember telling my wife, this is going to win somebody a Nobel Prize. Spoiler alert. My first book's called Losing the Nobel Prize. So it wasn't this guy, and it wasn't any of us, because it was retracted later on. As Neil mentioned, we had to go through the humiliation of, after being on the front page of the New York Times, press conference at Harvard, a real show all around the world, CNN, everybody.
So what was your academic affiliation at the time?
So I was a professor at UC San Diego.
Where you are now?
Yep,
Gotcha.
correctly.
Okay.
I've been there 21 years.
So they probably were running with this.
Oh yeah, we were on the front page of the most important paper of record, the San Diego Union Tribune, which
the Union Tribune.
I was on the cover of it. Yes, exactly. So that discovery launched into motion what would become the Simons Observatory, because that day I got a call from Jim Simons. He had already been funding a predecessor experiment of mine called the Simons Array, which is a small grouping of telescopes meant to also look at the same signals, but other signals too. And he called me up in that distinctive voice after smoking Merit cigarettes without filters. for 60 years. He started smoking when he was in his, late teenage. So
Right.
don't do that out there.
Chain smoker.
Doctors about, he was a chain smoker.
Hey, Brian, how are you?
Exactly what he sounded like, but more Boston.
I just got
Chuck,
done.
more Boston.
Oh, I can't do Boston.
Plus, it doesn't sound good in Boston.
Oh, that's wicked.
Like,
Wicked.
it does. That's the diner waitress voice, man.
Yeah.
Brian Keating and his team are helping us piece together one of the biggest puzzles in cosmology, dark matter and energy. But new findings may be shaking up everything we thought we knew. Data suggests dark energy might be weakening, meaning the universe's expansion could actually be slowing down. If true, it would challenge one of the biggest assumptions in modern physics. But before we rewrite the textbooks, we need clarity. That's exactly why StarTalk continues to partner with Ground News. They built an app and website that helps us separate speculation from science. With one swipe, we can find original research and highly factual sources covering the most complex breakthroughs in cosmology. They were actually founded by a former NASA engineer with the same level of precision you'd expect for space missions. But the best part? Ground News isn't some new tool to learn. They're a smarter, better version of how you're already staying informed. So follow every major development from dark energy to deep space with interest pages tailored to the topics you care about most. We're giving our viewers 40% off the same unlimited access Vantage plan we use. Just go to groundnews.startalk or scan this QR code to bring the cost of context and clarity down to $5 a month. Now, back to the show.
So we left off in your complicated life where you had the Bicep 2 experiment that reported what would later be determined to be an erroneous detection. Meanwhile, Jim Simons, seeing what you're seeking, wanted to participate in that, puts you head of an early version of the Simons Observatory, some variant, Simons Array.
Similar, yeah.
But then the Bicep 2 result comes out.
That's right.
Which is not good for him.
That's right.
Because Bicep 2 is leading the world to, well, we think has discovered these ripples.
Yeah.
Exactly.
But really they haven't. But he doesn't know that.
That's right.
So he's like, bro, what's up with my money?
Right. Okay.
I want it back. So he calls me up and I'm like, I don't know what to say because I knew in the back of my mind there could be problems with the result and we might need to confirm it with another instrument, which later turned out to be the case, or that we were actually right. And maybe I might have to say, look, I got to give you back your money. I got to have some integrity and, and refund your money, so to speak. And I was going crazy because where do you get, $10 million and give it back to
that's
on
what
a public university?
Let me tell you something. That's when I just ran out of integrity.
You ran out of money and integrity at the same time.
Ran out of town. Ran out of
$10 million, no more integrity.
So then how was it determined?
Yeah.
Because I remembered this.
Yeah.
I wasn't close to it, but it was
right.
happening. It was an important episode in science.
Yeah.
Actually. Okay, so now pick
Let me
up
say
the
why it's so
action.
important
And
first.
can I, before you
go
even
ahead.
get there, can you tell me exactly what was missing from the discovery that invalidated?
Absolutely. Let me take one giant step back. Why are we doing any of these projects to begin with? So looking for gravitational waves. Take yourself back to 2014, right? We hadn't detected, LIGO had not made its detection
Right.
of gravitational waves.
Obama was president.
Ukraine had not been invaded the first time.
Hold on, guys. Give me 1 second. I'm staving off. Once he said Obama was president, I'm like, oh, God.
The elevator had not been ridden.
What have we
Escalator.
done? Okay, go ahead.
Go. Yeah.
How to annoy Chuck. So at that phase, we had not detected gravitational waves directly,
Right.
as LIGO had.
Right.
We had an indirect evidence that they existed, but there was a theory that had been promulgated since the early 1980s by Alan Guth. So the inflationary theory is the answer to the question, what caused the Big Bang? What made the Big Bang bang? And the postulate is that there's a so-called quantum field that filled the whole universe, that fluctuated out of nothing, and the universe came into existence.
As quanta do.
Yeah, exactly.
They do stuff out of nothing all the time.
They are the magicians of the universe.
Yes. Everything quantum.
Watch me pull a universe out of my hat.
That's exactly what they're doing.
That's right.
Let me birth the universe over there on a fluctuation.
There you go.
All right.
So this discovery, if it were true, if it were confirmed, would be tantamount to discovering the Big Bang itself. 2012, which it was done not far from here by Penzias and Wilson, discovery of the CMB, the cosmic microwave background, which is what butters the bread around the Keating house.
Penzias Wilson at Bell Labs in Jersey.
Exactly, not too far from here.
By mistake too.
By the way, it's across the Hudson River. That makes it far.
That's right.
Okay,
that's
I know
right.
you're in here from San Diego.
Don't listen to
I'm
this
a Long
guy.
Islander.
He's a Manhattan.
I'm a New Yorker.
snob.
Yeah,
No,
that's
he
right.
lives in New Jersey. So
That is true.
you got Long Island roots?
Yeah.
What town?
Stony Brook. Yeah.
Don't he? Oh my God!
That's right. Yeah, that's where Jim and my dad were professors.
Oh, that's why that would be the case.
So
Okay.
so inflation. So we claim that we discovered this. So that's why everyone said this is going to win a Nobel Prize, because
Right.
they won a Nobel Prize for discovering just the heat left over from the Big Bang.
Right.
All the more so for discovering what ignited the spark that ignited the Big Bang.
Wow.
So that was why I designed Bicep originally. Then it became Bicep 2, like the iPhone gets new detectors, cameras. We upgraded it. So we ended up building this telescope. And then when I got this call from Jim Simons, I was in this pickle, right? Because I don't know what to say. I kind of invented, I was kind of the father of the predecessor experiment to Bicep 2, Bicep 1. And I was definitely the father of that. And then I was involved with this new project that he was funding. Now, what ended up happening was we had relied on data, not from our own instrument. Actually, someone had taken a picture of a PowerPoint slide from our arch nemesis, the Planck experiment. So the Planck experiment is €1 billion experiment. Bicep was a mere $10 million US dollar.
The European Space Agency.
You're out at L2 at Lagrange Point, orbiting around the sun and the Earth, the farthest, coldest, deepest, darkest. Incredible team, 1,000 people working
So
on it.
Earth Sun L2.
Earth Sun L2.
That's
That's
where
right.
JWST is.
Yeah,
Right.
exactly.
Yeah,
Yeah,
yeah.
It was one of the first. It was the second one after
They're hanging
Wilkinson.
out.
They're just
Just
parked
chilling.
Yeah,
They're
that's right.
chilling.
Like they're on stakeout. Two cops on stakeout, sitting there at L2.
Should you go for coffee this time? I went for coffee last
And it
time.
is true because they're like
Yeah.
parked
They're
there.
parked there.
Yeah, as
Yeah.
Earth orbits the sun.
Think about getting a validation out there. I mean, that is not easy. So Jim calls me up, what's going on and what to do next. So we ended up discovering that we didn't see this pattern that would be the imprimatur of the Big Bang. We didn't see this cosmic swirling curls from the Big
Who
Bang.
determined you didn't see it?
We, along with our competitor, the Planck teams, we worked together to find out that actually what we saw was nothing more than some cosmic schmutz.
Right.
Some dust.
Dust.
It was, yeah.
The
Cosmic
people who
dust.
study dust, so don't call it
Absolutely.
schmutz.
That's right.
Right.
To them, it's their livelihood.
One astronomer's dust is another astronomer's
Schmutz.
lost Nobel Prize. So it wasn't a blunder, Chuck. It wasn't like we left, put our thumb over the camera or something like that. We actually measured exquisitely precisely this signal that is astrophysical in origin at the billionths of degree Kelvin level. I mean, it's an exquisite measurement.
But it's a local signal, not a
Exactly.
Big Bang
Just
signal.
happened to be a different
Exactly.
signal.
Exactly.
That's all. So
So congratulations on the precision of the
It
measurement.
is. It actually
You
still is.
idiot interpreting it the wrong way.
However, what it did was it's like, oh, this thing works.
The experiment
That's
worked.
basically
That's right. It's the most precise measurement of what's called an astrophysical foreground. Something in the foreground, in the space between you and the cosmos, that is made in the astrophysics. It's actually the same material that makes up meteorites, and I brought some meteorites for you guys here. So dust is ubiquitous, and the same type of dust that obscured our measurement and prevented me from winning a Nobel Prize is actually the same stuff that the planets are made of. And so it's identical to that. Happens to be magnetic, and it produces radiation and heat, and so we saw it, and we misinterpreted it as the signal from the Big Bang.
Produces infrared.
Infrared and microwave emission, yep. So Jim Simons, upon hearing this, he's like, well, what do we do? And then when we retracted the claim that we had detected inflation, humiliating. And this is not like an easy thing to do.
Right.
Still, he said, I want to go for the signal more than ever now, but we have to remove the dust. So it's a good thing, like you said, Chuck.
Yeah.
It's actually a good thing. When you make a mistake, you say, oh, I got to refine what I do. It's like you go out to your car, there's dust on the windshield. I got to clean the windshield.
No, except you're not going out to the galaxy and removing the dust. You're removing the dust signature in your data.
Exactly. So
Right.
how do you do that without a vacuum cleaner or a dust devil?
Yeah, you
whatever?
need ways to do that.
Exactly.
Yeah,
so
yeah.
so what Jim was wise about, and what David Spergel had figured out, because he was one of the ones that killed off the Bicep interpretation, he figured out we need to have multiple colors of light. Bicep 2 only had one color of light. We couldn't see multiple colors.
Right.
And when you have multiple colors, you learn about the spectrum, you learn about the characteristics. So what Simon's Observatory now does, and why Jim funded that, is it can see the cosmic signal. If it's there, we have to assume it may not be there just because we want it to be there, but it can also see the dust. And when you have the signal, you have the cosmic signal plus the dust signal. We have a telescope that just
So what you're
measures
saying,
dust.
in your one band of light,
Exactly.
you
Yes.
could not distinguish the cosmic signal from the local signal.
Yes.
In two bands of light, they each will show up differently in two bands.
Exactly.
And now you'll be able to identify.
And now you've been able to take it
That's right.
and take it out.
That's right.
But that's not what I remember most about this episode.
Okay.
I remember the ambulance chasing theorists who came behind this false result thinking it's real, coming up with an explanation so they can get their Nobel Prize too.
That's right.
Wow.
That's right.
That's what I remember.
Yeah, I got
It was like
emails,
100 theories. How many theories?
Well, there's 1,800 papers published about it. It's my most cited paper, embarrassingly enough. But yeah, so it led to this disaster in some sense led to the initiation of this new most powerful instrument ever made to do the cosmic microwave background.
And that's the Science Observatory
Now,
of which you are PI.
Yep.
Well, congratulations.
Yeah, thank you very much. Yeah.
That's very cool, man.
Yeah.
That's a great story.
Yeah.
All right.
Thank you.
Well, we
You
got
should
to
write a book
we got to
about
get to. Oh, he should write a book about it. We're all familiar with Polaroid sunglasses, and some subset of those who own them know what they're doing. But I think most people don't.
Yeah.
It's just a type of sunglasses that you want.
Yeah.
I always have polarized sunglasses with me in my backpack just because you never know when you need to
We need to hide from the paparazzi. And their flash might bounce off of something, so I need polarizing sunglasses to block out that bounce light.
So catch us all up on how and why polarized observations work.
Yeah, so light has three primary properties. Its color, spectrum, its intensity, how bright the light is, and also something called its polarization, least familiar property of light.
Right.
And light is an electromagnetic wave. So when a wave oscillates, the plane that it's oscillating up and down in, the electric field vectors are going up, down like that, and the magnetic field vectors are going like that.
So it's two waves. One's going up and down, but the
Electro-
other,
That's right.
one's going up and down,
the
and the
electro
other
part.
one is going side to side.
Magnetic
and
part,
that's the
electromagnetic wave.
Electromagnetic.
Right.
Okay.
And when light interacts with matter, you see like a glare, you see a reflection there. Well, what polarized sunglasses do is that they oppress and suppress one of those.
Not oppress.
Come on.
You see, you're sitting between two people here who take
who
a
were
different
oppressed.
understanding
Okay, fine.
of that word.
All right, fine.
I sure does know that one day
That's right.
we's gonna be able to get through.
See the mountaintop.
See the light using the polarized sunglasses.
See the other side.
You know, sometimes I just feel tired, like I'm tired light. Tired light.
Oh man, we got to get all of this into the B-roll. All right, good. The way that polarized sunglasses work is that they actually suppress one of the two polarization states of light. It happens to be the horizontal one, and that's why you want to wear them at the beach or you want to wear them when you're driving because you get that
Or skiing.
glare. Or skiing, yeah,
Especially.
absolutely,
Yeah,
yeah,
that's
absolutely
right.
when you're skiing, and that's why they're more expensive because you have to add this film that has molecules that are actually made of polymers that actually suppress one of those two states of light, but let the rest in because you don't want to be totally dark.
Right. Go ahead.
So polarized sunglasses suppress one of the two polarization states of light. They make the light 50% darker. Also in photography called neutral density filter.
Neutral density filters.
Exactly, yeah. So the film that's on these glasses actually knocks out one of the two polarization states of light, the one that is responsible for the glare
the
that
glare.
you see. So that means if you have two of them, and if they are oriented just
So let's
right.
try that. So here's some light coming through.
Yeah.
Okay.
So this is a very expensive demo here. So this is actually knocking out half of the light in there because only half. It's an unpolarized source, so half of it's polarized one way, half of it's polarized the other
The
way.
source is unpolarized.
Right.
Mhm.
And then if you put another polarized source in front of it, and as I rotate it, eventually the axis of polarization will be orthogonal, and that will block out 100% of the
Perpendicular.
light. Do you see perpendicular?
There it is.
So now it's completely orthogonal or perpendicular, as you would say. And then as I rotate it slightly the off axis, now it lets in some of
It
the light.
lets the light through.
So that's how polarization works. That's why you can see through the glare. It doesn't affect your eyes. It doesn't hurt your eyes when you're skiing, as you said. And so that's what these instruments are doing. They're looking for polarization, not of optical light, but of microwave light from the Big Bang, the leftover heat from the Big Bang. So remember I said inflation. Inflation is this theory that there's this quantum field that fluctuated, that produced everything that we know and love about the Big Bang. It would also produce what are called gravitational waves, waves in the fabric of space-time itself. Those waves would perturb the electrons, the protons, the early hydrogen atoms in the universe when the CMB, or cosmic microwave background, was produced about 400,000 years after the Big Bang. When light interacts with matter, as you see from the glare, it becomes polarized. That matter would be polarized. That matter in its orientation would change depending on how much gravitational wave energy was present when the CMB was produced. So it's actually a gravitational wave detector. We're using the photons of the cosmic background as a type of film, if you will, and onto which these waves of gravity, if they exist, and only if they exist,
They get
they get a polarization to them, a curling, twisting pattern of polarization we call it B-mode polarization.
Wow.
So it's a lot of logical steps, but actually it's very well tested and very well theorized. It just hasn't been detected yet.
It's quality physics going into that. Yeah.
That's
Yeah.
super cool, man.
Yeah. Yeah, literally. And we can't use we can't use an iPhone. We got to cool our detectors down to my colleague Suzanne Staggs at Princeton. She's built detectors that operate at 0.1 degree above absolute zero.
Right.
Using isotopes of helium. And she does incredible stuff. And they're superconducting detectors. They're basically little thermometers. So, you go outside, and not in New York, but in San Diego, you go outside, you can see the sun with your hand. You can basically detect where the sun is using its infrared and that your skin can absorb infrared heat. Well, so too, we can have detectors that can see microwaves and infrared radiation, but they have to operate where it's really cold. Otherwise, it's like building, the biggest, James Webb Space Telescope and putting it in Manhattan.
And so what's the fluctuation of temperature that you're looking for between what the universe has cooled to and what would have been present right at the Big Bang?
Yeah, exactly what we're looking for. So there'll be deviations in about a part in a billion. So a nanokelvin. So in other words, if the universe on average is about 2.7 Kelvin, it would be 2.7 plus a nanokelvin in that direction and 2.7 minus 1 nanokelvin. So you're looking at the 9th decimal place, right? So
a billionth of a degree.
Billionth of a degree.
Okay.
Above absolute from.
Wait.
And somebody gave you money to do this?
Wait. So,
Wow.
so here's what.
That's insane.
Yeah.
So let me drive home why we need inflation.
Okay.
Okay.
Yes.
Because
Let me tell you why. Okay. Because we're going through a transition.
Okay.
in this direction, it's 2.7. Give me a few more decimal places.
2.726.
It's 2.726 degrees in that direction in the universe.
Okay.
And I look in the other direction.
Right.
It's 2.76 degrees.
Yeah.
Right.
And how the hell do they know to be the same temperature as each other
right.
to 1,000th of a degree?
Right.
90 billion light years
this
apart.
room,
Yep.
the temperature fluctuates by degrees.
Exactly.
By whole degrees. In this corner, that corner,
right.
over there, near a lamp. The whole universe is that.
That's right.
Just one.
And
bit-
so
one-
what Guth said was, the way to get that to be the case, when the universe was small and all talking to itself in equilibrium, temperature equilibrium,
Right.
then it quickly expanded.
Right.
Like so fast, it couldn't go out of equilibrium with itself. So it all has the markings of that same temperature from a bajillion years ago.
That's so cool. Hence, the justification for inflation. Yeah.
Yes.
Right. Because all of
Rapid.
that expansion
Okay.
all at
Rapidly.
once
Rapidly.
It gives you the uniformity
Yes.
across the entire expansion.
Correct.
Wow.
Correct.
Okay, I'm done.
No, we need you,
No,
Chuck.
no.
Chuck, it's a cosmic Aquarius.
This is
No,
crazy.
come back.
He's heading to L2.
He's going to L2. On the stakeout.
Oh my God.
Yeah.
That's insane.
It is insane.
I mean, that is literally, who thinks like this? Who thinks like this? Oh my God. Wow, that's brilliant. I mean,
Yeah.
that's really
So
cool.
the inflation explains it, but then we needed a cause for the inflation. And
Right.
we had to pull that out of our ass. What was that?
Basically, I mean, it results. It's related to what's called the multiverse. Basically, without the multiverse, you don't get inflation in most models, according to most people.
Yeah.
And that's causes some people like.
No, but there's a phase transition.
There's a
Right.
phase transition, yeah.
Yeah.
And the actual dynamics of it can be explained using quantum field theory, which is the theory everywhere in space. There's a quantum field.
Okay, you guys, right now, you sound like an episode of Star Trek. I swear to God.
Star Trek Next Generation. Next Generation.
Next Generation.
They have more quantum.
They love phase transitions and quantum.
Let's get to the questions
Yeah,
now.
yeah.
Come on.
Okay,
Chuck.
all right. Oh man, I got so excited. I put the hello, Dr. Tyson, Dr. Keating, 10-year-old Ruben, and 6-year-old Eli here from Harrisburg, PA.
All right.
If everything was compacted into one tiny dot, smaller than a speck of dust before the Big Bang, what indeed formed the dust? What was around prior to the Big Bang? Doesn't this mean that there was another universe that collapsed to form ours? So what's the deal?
I wish that those young people would have said, "I have a very simple question for you."
Yeah.
They're basically asking what caused the Big Bang,
caused the Big Bang?
It caused the universe to start expanding in the first place. So the mark of a good scientist should be, we don't know. We don't know for sure.
Right.
And there are
That's what he
alternative.
says when he doesn't know something. It's the mark of a good scientist when he doesn't know.
That's right. And my wife sends me to the
Not
grocery
the
store
mark
to
of a
get some.
crappy scientist who should have known and doesn't.
Right.
Okay, go on.
Well, that's why we call it research. My PhD
No,
advisor used to
what
say-
you mean is
Yeah.
it is not known in the
Exactly.
field.
That's right.
Not that you don't know it,
Exactly.
but perhaps you should.
We are trying to know the answer to that
We
question.
is the full community. Yeah.
Community of scientists, but specifically on the Simons Observatory. Their very question is the question the Simons Observatory is in part designed to answer. Was there any sense? Stephen Hawking used to say it's nonsensical to ask what happened before the Big Bang because time came into existence.
I was going to say.
He said it's like asking what's north of the North Pole, which we all know, Santa Claus, right? There's got to be Santa Claus up there.
Yeah.
But in reality, we can answer that question in the affirmative. As you actually hinted at, there could have been a universe that existed beforehand that actually collapsed in what we used to call a big crunch. Now we call it a bounce. They're actually some of the most eminent theorists on Earth, including those that...
I never like crunch because that implies it's brittle and it makes a crackling sound.
But it's cereal revenue.
And delicious. Anything with the word crunch in it, it's got to be good.
Cap'n. How do they punctuate that? So the actual answer is we're trying to determine not what happened, because in science you can't prove something happened. Like you can prove 1 + 1 = 2 or 1 × 1 = 2, as you tell our mutual friend Terrence. But in reality, we can't prove a physical fact, but we can falsify alternative models. So if we see this twisting pattern of polarization called curl modes or B modes, that will falsify the other models, that there was a big crunch, that there was a previous existing universe in a cyclical model. So we can prove those wrong. And getting more data about this, if we do see it, that would be the death knell for the alternative models, and that would be a huge triumph in the history of cosmology.
Okay, so you don't know the answer. Okay, next
there
question.
we go. All right, glad we cleared that up. All right, this is...
No, but it's good. It's good to know that floating ideas do have ways of being tested.
Exactly.
And rejected.
Because some things you can just conjecture anything, literally, like thousands of theorists did, that are consistent after the fact. But the key thing is to do it before.
You want a prediction, not a post-diction.
Exactly.
Ooh, look at that.
Retro.
Good day, gentlemen. This is Matt from Oklahoma. My burning question is about the origins of the universe. What exactly are we trying to gain by looking into the past? Will it help advance the population on Earth in a technological standpoint, or is it solely for the history books?
Well,
I got a feeling that Matt D has a little problem with your work.
But as polite as that was, he's really questioning your existence.
Yeah, that's right. Yeah, and I have to justify it to myself and the taxpayers as well. And I don't mind that. And actually, I want to ask you guys that as they step in, because Matt's not here. What's your favorite day on the calendar every year?
My birthday.
Your birthday. What about you, Neil?
I like the 4 cardinal points of the calendar.
Yeah, okay. So what are those?
The equinoxes and the solstices.
Okay.
That's right.
And you know what? When he was like, I like the 4 cardinal points, I was like, Jesus, Neil. But then I was like, oh my God, he actually does. Because as long as I've known him, he's the only person that points those days out to you.
Right.
Like if we're texting on that day, he will point out to you. Like all those days.
I look forward to those days because that's when he's on Twitter. I know that's the only time he's going to get
exactly. That's what I am. That's correct.
All right,
so go ahead.
Okay. So you mentioned it, and it's related to yours. So it's your birthday. What is a birthday? What is some people say Christmas, their anniversary, the kid's birthday, whatever you want. But it's a beginning. And why do you like that? Because you have no idea from first-hand evidence what happened before you were born, do you, Chuck? You have to rely on other people's eyewitness testimony.
Well, I had video.
Oh, my God. I don't want to see that.
No, he was reincarnated, so he has knowledge before.
He had his own big crunch, too. Yeah. So people want to know what happened before they came here. It's the ultimate in history, and that fulfills a need in us. Like, does knowing history create, some excess GDP or something? No, but it's part of being a well-rounded, educated, civilized society. Yeah. And knowing the answers to the big questions is what makes us different from the animals. We're the only people. Homo sapien means one who is wise. Not one who knows, it's one who is wise. So we have wisdom, that is to ask questions that perhaps have no answer, but that's what makes us unique and different from all other species.
Okay. Listen, I think
it's my existence, Justin.
I think you defended yourself well.
Yeah, okay.
All right?
We'll give him that.
So there you go, Matt.
Give me some more.
Here we go. This is Alan Rayer who says, hello, Dr. Tyson, Dr. Keating. I always wondered how and when will CMB last in our frame of reference? When will radio waves kick in? Should I say CRB?
Ooh, I like
good
that.
One.
Let me preamble that by saying radio waves at one point in our not that distant past included what would later be called microwaves.
Right.
And microwaves were simply small radio waves, microwaves. And they're really like a few centimeters, and radio waves are even longer than that.
Yeah,
so So historically, it's still radio waves.
Yeah.
But since we have a word for it, we use it.
That's
the
right.
small radio waves we call microwaves. Okay, pick it up from there.
So if you go out into the universe and you make a little box and it's 1 cubic centimeter, okay? Inside of that box will be mostly nothing. There might be maybe a proton or neutrino, but mostly there'll be 419 photons from the Big Bang, and they all have an average wavelength of about 2 millimeters on average. So there's a spread. It's a black body. So that 2 millimeter wavelength over time has stretched from much shorter wavelengths before that it was infrared, then it was optical, then it was ultraviolet, and eventually it was gamma ray. When the universe came into existence, highly energetic.
Wait. I don't think that was a photon that you can describe that way, moving through the volume before recombination, right?
Oh yeah, no, it was. Yeah.
You can think, can you?
Yeah, the recombination.
I'm thinking of the free photons since then.
Yes.
That's a temperature from which but you're saying we're okay.
We can extrapolate back to.
Well, you can go before that. It's just not a free photon.
It's not a
Okay,
free.
fine.
Yeah, it's scattering.
It's a scattered photon.
right.
Okay.
Just as you did that video recently, that's beautiful, about how long it takes for a photon to get out of the sun.
Oh yes. Okay.
Tightly coupled matter and radiation. The universe has been expanding and cooling, so eventually it will get into the radio waves. But keep paying your taxes because that's going to take billions of years. The universe has to go expand by more than a factor of 10 from where it is now, which could take more than a factor of 10 times the age of the universe.
Because the wavelength 10 times bigger is basically when we start calling it a radio wave. Okay. So the universe has to be 10 times bigger.
Right.
There's a stretching into the universe.
Exactly. Yep.
That's so cool.
So the answer is yes.
Yes.
Yeah.
You're just not going to see it, buddy.
I don't know if you want to spend money on the trademark of that patent right now.
But just to clarify, before it was the cosmic microwave background, it was the cosmic visible background.
Yeah, or infrared.
Or infrared background.
That's right.
Then the cosmic visible cosmic
optical.
Well, visible. And then ultraviolet on the other side, and with a cosmic X-ray background.
Yep.
And then gamma ray background.
That's right. Yep.
There you go.
Okay.
I love it.
Hey, StarTalk fans. I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version. And you can get that in Spotify and Apple Podcast and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic on StarTalk.
This is Yogesh Jog, who says, "Hello, Lord Nice, Dr. Keating, and my personal astrophysicist."
Ooh, I love that.
Yogesh from Nagpur, India. My question is the CMB anisotropy really random? For those who may not know, what is anisotropy?
It means not isotropic.
Right.
That makes sense. And why would it be and then? Not just, why isn't it just a?
It's just asotropic.
Right.
I don't know.
Well, anyway.
Okay, so tell me about isotropy.
Yeah. So isotropy is the feature that you have complete uniformity and things look the same and they are the same. Homogeneity, it's similar in
every
composition.
direction.
In every direction that you
No
look.
matter which way you point the telescope.
No matter what.
Yeah. So if you're ever flying on an airplane and you're in the
You
clouds.
go through a cloud.
And you go through a cloud.
Yeah. And that cloud, to you, when you look out the window, it looks perfectly isotropic. Anywhere you look out the window. And if you're in the cockpit.
It's the same brightness.
It's the same brightness. It kind of looks like you're inside of a ping pong ball. Everything is the same brightness and intensity. That's isotropic. That's perfect isotropy, the principle of looking the same everywhere. But anisotropy just means fluctuations from that amount.
So it's not that.
It's not that.
You look in one space, you'll see something different than you look in the other space.
That's right. Now, if the universe were perfectly symmetric at earlier times, the amount of matter was the same everywhere, the amount of dark matter was the same everywhere, any exotic particles, everything was exactly identical, the universe would have no way to know where it should form a cluster of galaxies, a single galaxy, a planet, et cetera, right? So if you had perfect isotropy, and Isaac Newton realized this 300 plus years ago, perfect isotropy is incompatible with our existence because we don't see perfection wherever we look. We aspire to.
We also know that there's clumps of dark matter.
Plus, we know that we exist.
We know exactly.
Exactly.
So it's kind of what's called
We are clumps of matter.
We are clumps of matter ourselves.
So the question's Yogesh is asking what is that significant of? And it's basically related to the fact that we formed in a region where there was an excess of dark matter.
Right.
Where did that excess of dark matter know where to coagulate, though? That's where inflation comes in. Because all fields, all quantum fields, have tiny fluctuations in them. They are not isotropic either.
Quantum physics enabled this universe.
That's right. We are quantum fluctuation. We are the product of quantum. If inflation's right, we shouldn't presuppose that it is. But we're looking to see if there is. So that those pools of dark matter knew where to coagulate because of the fluctuations in the quantum field.
So now these fluctuations, are they disruptions in the field itself that create something pops out of the field? And that's so the universe itself, is it just one big field?
According to some, that the universe is in a particular instantiation of these conditions of our quantum field in what's called the multiverse. When we were kids, there was just a universe, right? Now there's a multiverse, which some say should be more encompassing. Just as we know we're just one star, one planet, there's many, many billions of galaxies. There could be trillions or an infinite number of universes, but where do they inhabit? They inhabit the multiverse. The multiverse is the collection of all points in four-dimensional space-time, and maybe higher space-time, that could, will, or ever will exist. So so we are a fluctuation in that greater space. You're absolutely right. And then within those fluctuations, it's like waves in the ocean. They're waves upon waves upon waves. And we are the manifestation of this infinite series of wave trains that perhaps dates back to the Big Bang itself.
So Chuck, as insulting as it sounds, to accuse someone of being a fluctuation is actually quite the compliment, cosmically speaking.
Look at that. All right, good question there.
Time for just a couple more.
All right, questions. This is Brandon Christian. Brandon Christian says, hello, Dr. Tyson, Lord Nice, Dr. Keating. This is Brandon from New Jersey. My question today is, do we have any idea what could possibly be on the other side of the CMB? Would it be considered a part of our universe if we were to discover it, or would it be something else altogether?
Okay. So the CMB is the shell of photons. It's a fictitious shell of photons that are coming to us from a particular event.
What do you mean fictitious? Does that word show up in your sentence?
Well, because it's an artificial, there's no place you can go where the CMB is, which is what the question is asking, right? The CMB is a representative of an event that occurred. It's the event at which the very first electrons fused with the very first protons, making the very first atom, hydrogen. When that happened, the universe became transparent to those waves of light that were existing beforehand. Those waves of photon then can free stream and come towards our telescopes. They come in all directions. So it's a moment. As you look back in space, you're looking back in time. So it's a moment in time, and it looks like a shell to us. We look out and we see a shell of photons, a little bit hotter here, a little bit colder there, but on average, 2.726 degrees Kelvin above absolute zero. There are tiny fluctuations in that. So beyond that just means earlier in time. So yes, there were things earlier in time, but it was a pretty boring life. It was a pretty boring before that 200.
It's nearly 400,000 years before that.
Yeah. So for 400,000 years, there was nothingness except for there was protons and neutrons and plasma and so forth and electrons, but there was no cosmic event. There's no place. There's no there.
Well, the universe was just glowing at these different temperatures.
Exactly. It was a plasma. It was almost uniform plasma.
Right. Okay.
Expanding, cooling, and then shifting in wavelength, redshifting and wavelength.
There you go. Wow.
All right.
Super cool. This is 1701 Kara, who says, greetings from Tennessee, Dr. Tyson and Comrade Nice. Why you gotta make me Russian? I have a cosmic query regarding the Higgs field. Is the current model of the Higgs field evenly distributed? Or could there be areas in space-time where the field is more dense?
This is a great question.
Ooh, I like that.
That's a really
Could that mean
good-
that it's giving different masses
At
to
different-
particles over here than over there?
Yeah.
Wouldn't that be wild?
That'd be a messed up universe,
That's
though. What mass are you? Well, today or yesterday? Right.
So a good friend of mine, Matt Strassler, guys should have him on. He wrote a wonderful book about this called Waves in an Impossible Sea, and it's all about the Higgs field. I'm glad that
You just like that impossible word.
I know,
That's
I love
all.
it. You'd be surprised how many books have the word impossible in it. So the Higgs field is what, and that's why it's impressive. Most people talk about the Higgs boson.
Right.
That's not what's so fundamental. The Higgs boson is just one instantiation, one creation moment of a particular fluctuation of this field called the Higgs field.
Right.
Yes, it could vary from time to time, and the most exciting thing is that it's what's called a scalar field. I don't want to get too technical, but that's the first and only scalar field that we know about. The other one that's postulated but not known yet to exist, we hope we can, shed some light on it, no pun intended, is the inflaton field. Those are scalar fields. They don't have what are called vector properties. They don't have properties. They only have a value. Like the temperature in this room is a scalar. It's a point. Every point in space, there's a value. 30 degrees Celsius. It's kind of hot over here. I'm talking. It gets even hotter. But the point is, it's a number at every point. But the Higgs field is a special case like that. The other types of field, like fermions, quarks, and other types of fields in photon fields, they are not. They have a sort of direction at each point in space-time. So the
Like a
Higgs
gravitational field has a value and a direction that it wants to pull
right.
you.
Yep. Yeah.
Right.
So this just has a value.
Exactly.
Okay.
Okay.
Yep. So
So why do we care about that?
So if it did vary, it could be connected the Higgs field and the inflaton. So that would be really exciting. It would say that the field that is responsible for giving inertia and mass to massive particles was in existence and coupled somehow to the origin of the universe itself. So maybe there's some connection between the masses of all particles that were, are, or ever will be, and this initial phase of the universe called the inflation.
Something we haven't figured out yet, because all the masses look pretty random.
Yeah.
I mean,
We have no fundamental theory that predicts why this
of
may
the
be.
masses of particles in the universe.
Yeah, exactly.
Okay.
That's a great question.
All right. Eric Venus. And he says, yes, like the planet and the goddess. He says, I understand that as we look further into the universe, we're looking further back in time. What have we learned so far about the early universe that we can expect to impact life on Earth in the near future? So is there anything looking back that we can use looking forward?
I like that.
Yeah. So there's a lot of mysteries that we still don't know about. We don't know how the very first galaxies formed out of nothingness that was left over from the CMB. We don't know exactly how they went through this transition. It's called the cosmic dark ages. So just as we learn about history, we learn about the actual medieval dark ages that impacts decisions that we can make as a society. So too, I think learning about how the early universe evolved, the types of physics that were in play, and yes, if there is, as some hinting. There are some hints that actually some of the bulk properties of the universe, most particularly dark energy, is evolving. We need to know that. We need to know, was it different in the past? Was dark energy different value than it has today? Was the Hubble constant
If you thought
different?
it was constant for the whole universe, we now might be true that it has changed in the past, it could change in the future.
Exactly.
Yeah.
And that could involve the properties of the space-time itself, it's called vacuum energy of the universe itself. And that could lead to, again, a different scenario for the end of the universe. Everyone always talks about the beginning of the universe, the big rip, the big crunch. We don't know what would happen. But, as I say, keep paying your taxes because it could be another trillion years before we find the answer.
And I had another fast bit to that. It's not as dramatic as your answer, but I came of age when we had catalogs of peculiar galaxies. And they were called peculiar. We didn't know what the hell they were. Only in the era of computing were we able to simulate what must have happened to ordinary galaxies to make them look like that, because they were colliding with each other.
Yeah.
Train wrecks. And so once we learned that had happened in the past to create this catalog of peculiar galaxies, we now say, wait a minute, we're headed towards Andromeda. We're going to be one of these simulations that somebody else says, hey, Dave.
Right.
Some future graduate student.
In the future, say, hey, look at those two galaxies over there. Isn't that beautiful?
Wow. Why? Look, they didn't always look like a sombrero.
Why are there so many Kardashians in that in Milkdromeda?
Okay, one more. Last one.
Matt Newcomb says this. Hello, Dr. Tyson, Dr. Keating, Lord Nice. My name is Matt Newcomb, like Duke Nukem, and I'm from San Diego, California.
San Diego, that's your hometown.
There you go.
I mean, your current hometown.
I'm curious about Simon's observatory ability to detect new particles. How do you know what to look for, and how does it collect that data?
Ooh, very
Cheers
good.
from a fellow science educator.
Yeah, come on my lab.
Can you discover things you're not looking for? That's a side light to that question.
Can you predict serendipity? So the CMB itself was discovered accidentally. They weren't looking for this glow of the Big Bang, its aftermath. So it's actually great. But what I love about the Simons Observatory is that there are things we're swinging for the fences on. We don't know if inflation took place. If we see it, it could be the same hullabaloo as happened with Bicep.
But just for our international audience, when you swing for the fences, it's a baseball reference.
Yeah.
And it means you're swinging for a very deep home run. And so you might strike out.
Yeah.
When you swing that way, you might strike out. But if you connect, all the way.
So yeah, for international listeners, think a cricket century. That's what.
Oh, is that it?
Look at that.
Excuse me.
That'll be even better. Look at that. So we're going for the cricket century, if you like. But there's things that are guaranteed to happen. They're guaranteed to know about. And that's the only particle of dark matter. Do you know that we've detected dark matter? There's dark matter detection. It's called the neutrino. Neutrino has every property of dark matter. It just doesn't make up enough to so-called, make the universe flat and so forth. But we've detected dark matter. However, embarrassingly enough, shamefully enough for physicists, with their 17 elementary particles, we don't know the mass of 3 of those 17. We know the mass exquisitely accurately for the other 14, the Higgs boson, the electron, etc.
What don't we know?
We don't know the mass of the 3 types of neutrinos, the 3 neutrino flavors. We have a lower bound and we have an upper bound. We don't have a measurement. It's like someone looking at Chuck and saying, "Oh, you're somewhere between 1 inch tall and 1,000 feet tall." Like it's interesting,
It's
but
true.
it's true.
But not useful.
Yeah, it's not
useful.
true, but not useful. That's a beautiful way to phrase it. So what we're going to go after is because we can take these early images of dark matter and the composition of the universe that is affected by them, we can effectively weigh the neutrino by getting enough of them together. They're very light. They're a million times less massive than the electron, at least. They could be even less. We can, for sure, constrain their properties, weigh them, if you will, but only by collecting them on the universe's most grand scales. Literally, to weigh enough of them, you need to measure a huge fraction of the universe's volume. And that's what we're going to do. So we're guaranteed to make an imprint on that and detect not new particles, perhaps, but we could possibly detect new particles. We just don't know if they're out there. And that's why serendipity is so hard to predict.
Wow.
That sounded like one of Yogi Berra's predictions. It's hard to make predictions, especially about the future.
When you come to a fork in the road, take
it. Yes. There you go. This conversation about the beginnings of things reminds me just of how interesting that question is. We can spend all our lives studying what is, what already exists, what will become of what already exists. What makes that scientifically accessible is that you can find some other object that's like it and do a different experiment on that to check for what properties it has, check for how it will respond to whatever you do to it, to see what it becomes in the future. We can do all of this. That's what most of science is. But there's a subset of scientists that are not content with knowing what something is or what it will be. They want to know where it came from. What are its origins? Sure, we did it for the Earth. There was a day we didn't know where the Earth came from or the sun. We found other planets. We found other stars. We see them being born, and our star looks like that. We say that's probably how our star was born. Okay, how about the galaxy? Well, we've got JWST helping us there. How did galaxies form? There's a point in the early universe where all that would have happened. We got top people working on that. But you keep doing this, and you reach a point where, well, how did the universe begin? Is there another universe to compare it with? No. Is there some, no. What do you do? We say, well, maybe there's a multiverse. That would account for a beginning of our universe. But then, all that does is push the origins question back one more notch in the past. Fine, you can tell me how this universe got here, now tell me how the multiverse got here. And whatever made that, tell me how that got here. That's what makes questions of origins so challenging and so fulfilling when you finally arrive at those answers. And that's a cosmic perspective. This has been a Cosmic Queries CMB edition.
That's what it is.
That's what it was, that's what it is, and that's what it will be. Brian, thanks for coming.
Thank you.
All right,
guys
and
so
we can
much.
find you online where?
BrianKeating.com/StarTalk. I've got some special giveaways from your listeners as well.
Whoa.
What?
Look at
Not
that.
Mars meteorites, but other types of meteorites.
What?
He's the only guest that comes here and leaves swag. That's amazing.
Well, I love what you guys do. Seriously, I love what you guys do.
Excellent.
You do
Well,
the
thank
most
you.
important thing, which is to teach the audience, teach the public how important science is to their lives.
Yeah. And you also, your book that you...
Losing the Nobel Prize.
Losing the Nobel Prize.
Into the Impossible, Think Like a Nobel Prize Winner. And then in the fall, coming out on my birthday, September 9th, is Focus Like a Nobel Prize Winner. It's a self-help guide for STEM nerds like me and Neil and maybe like you.
Sounds like the publisher's milking that subtitle there.
Yeah,
Go through life like a Nobel Prize winner.
Right.
Yeah.
Drive like a Nobel Prize. Exactly.
Cook breakfast like a Nobel Prize winner.
Exercise like a Nobel
Hey, you guys
Prize.
are giving me ideas. I got a franchise here.
That's all you
Thank you guys. You guys can do the blurbs on the back.
Yeah, you need to come up with one that says, lay on the couch and watch TV like a Nobel Prize winner. That one will be a bestseller, I guarantee you. I guarantee you that.
All right. Chuck, Brian, always good.
Always a pleasure.
Till next time, this has been StarTalk, Cosmic Queries Edition. As always, I bid you to keep looking up.